Hi, I'm Ryan Riley, Director of Flight Operations and Customer Success at GRYFN. Today, I'm excited to give you an updated walkthrough of our revolutionary software, the GRYFN Processing Tool. The GRYFN Processing Tool is your go-to solution for streamlining your workflows, enhancing efficiency, and unlocking valuable insights. In this demonstration, we'll explore the tool's intuitive interface, powerful features, and seamless integration capabilities. By the end of this demo, you'll understand how the GRYFN Processing Tool can transform your remote sensing operations and empower your business to achieve new heights. So without further ado, let's dive into the GRYFN Processing Tool. The GRYFN Processing Tool is a powerful software solution specifically designed to process raw sensor data from hyperspectral line scan, LiDAR, and high-resolution frame cameras, converting raw sensor data into orthorectified products such as geotiffs, NV rasters, and last point clouds. The GRYFN Processing Tool starts by bundling raw sensor data and their associated metadata into a single consistent, organized folder structure called a GRYFN Raw Data Bundle, or GRAW for short. By storing all raw sensor data and relevant metadata, GRAW bundles make for an excellent definitive archival source and structure. Let's step through the bundling process. To begin bundling data, we can select the Bundle Data tab on the left. From here, we have three options: create a new GRAW bundle, add data to an existing GRAW bundle, or for supported systems such as GRYFN Gobi, a GNSS, LiDAR, VNIR, and RGB system, we can query and download data directly from the sensor for automatic bundling. Today, we'll use the Create New Bundle option to fully walk through the process. On the first page of bundling, we can see the required inputs for the bundling process, a GRYFN system calibration file, and a path for the raw data. Let's start by selecting the system calibration file. This file denotes the lever arms and rotation angles between each sensor in the IMU and is generated by GRYFN uniquely for every system. You can see information like serial number, calibration date, and our lever arms and bore sight angles. Now there are two options to select the raw data to include in the bundle: single source and multi-source. In single source, we can select a single directory containing raw data. The software will parse this root directory and all subdirectories for all data files relevant to the sensors contained in the system calibration file. With the multi-source method, we're able to individually select directories for each data type. I've set up our raw data directory for this demo as subdirectories of this root folder, so we'll use single source today. The logs directory allows us to select a single directory to bundle any additional files in any format we may want to include in the bundle. The logs directory will not parse any subdirectories. If we have multiple flights that should have their data combined into a single output, we can add flights and select their raw data sources. Moving on to the optional parameters page, we have options such as processing extent, pilot, location, and notes or other information such as weather conditions. The processing extent can be a KML, shapefile, or GeoJSON that can be used to trim the extent of our final data products. Lastly, we can name our bundle and select a save path. For this demonstration, I'll name it with the date and the word demo. Now we can create the bundle. As the bundling process begins, we can see a progress bar on the left side in the job queue, as well as an elapsed time for the bundling job on the right side. Here in the File Explorer, we can also see that the GRAW bundle is being written into the directory I specified. We can see now that the bundling job is complete and have received a system notification. If we scroll to the bottom of the log, we can see the bundling process took about 30 seconds. After this process is complete, we have an Open Data Bundle button here that will open our File Explorer to the GRAW. First, in the root directory, we can see a few text files: our system calibration YAML. We can see that the sensor IDs in this file correspond with the folder names in the GRAW. A hyperspectral manifest YAML, and our mission data YAML, which contains paths to each of our bundled sensors, checksum values, and the optional metadata we added. Going back, we also have our processing extent file. The pipeline folder stores the pipeline YAML, which contains paths to each of our input types. You can also see the radiometric calibration section at the bottom. For systems with supported hyperspectral sensors, we can point GRYFN Processing Tool to our radiometric calibration files, allowing the software to bundle those in and perform raw to radiance conversion on the fly. This is currently supported for the Headwall Nano HP V-near sensor, Headwall SWIR sensors, and the Specum AFX10 V-near sensor. We also have a bundling logs folder which contains the output logs from the bundling process. Now that we've bundled the data, let's take a look at processing. We can go to the new job section of the software here. We're greeted with the option to select a pipeline, which is the set of instructions for how to process the data and which products to generate. You can see a list of different pipelines I've previously saved in the software, but for today's demo, we'll create a new one. First, we'll add tasks for each sensor in the system we collected data with. For this system, that's LiDAR, v-near hyperspectral, and RGB. We can open each sensor task to see the processing configuration and add products. Starting with LiDAR, we can edit processing configurations such as the laser range and laser azimuth or field of view. If we go down to products to produce, we can add a few data products. For this pipeline, we'll generate a digital surface model and a point cloud, but we can also generate a terrain model or height above ground point cloud. After adding our products, we can expand each product to see the product configuration. For the surface model, we can adjust parameters like the resolution or height percentile. You'll also notice with every product that we can change the product name and the extent options. We can either use the processing extent we bundled in, use none to process the full extent of data, select an extent file saved somewhere else on disk, or we can use the v-near extent if available. For Headwall hyperspectral sensors, typically data is captured using a KML polygon. These polygon coordinates are saved to a file with the raw v-near data, and we can use that file to trim our products if it's available. Use processing extent is the default option. If no extent is bundled in and this option is selected, the software will process the full extent of the data. For the point cloud, you can see we have the same extent options as well as an outlier removal option. If we move on to the v-near task, we see the process configuration is a bit different with parameters specific to this sensor type. The default settings for each sensor will work perfectly for 99% of use cases. The only thing special we need to do here is select a digital surface model for the orthorectification process. Since we have LiDAR with this system and are generating a digital surface model, we can select that product. Terrain models also work well, especially in environments with high relief. Two other surface model options are available. We can set a fixed value above ellipsoid if we have a very flat scene and know the ellipsoidal ground elevation. We can also select a surface model on disk, which is helpful if you don't have LiDAR in the system and want to select a model from publicly available sources like USGS, or if you have a photogrammetric surface model from another UAV system. A few other parameters I'll call out. Use radiometric calibration will apply a radiance conversion to the raw files when enabled. By default, we do this radiance conversion on the fly, but we can also write out the unorthorectified radiance cube with this toggle. And finally, we can write IGM or input geometry files if there's another software you'd rather use for mosaicing. Moving on to products, we have two types, orthomosaics and orthorectified flight lines. We can generate each of these products as either NV rasters with full spectral data or as 3-band mosaics for quick checking the data. We'll output just the NV orthomosaic and individual flight lines for this demo. Here we can select a resolution method, either allowing the software to calculate the maximum resolution possible based on the trajectory and surface model, then selecting a percentage of that value, or by setting a fixed resolution. We can also change the spectral binning, scale factor, and data type. You can see we have the same options available to us with the individually orthorectified flight lines. Lastly, we'll look at the RGB task. RGB has the same configuration with an initial processing configuration and a set of instructions for producing products. We'll generate an orthomosaic and colorized point cloud in this pipeline. You'll notice, like with the hyperspectral task, that our RGB products, we must select a LiDAR product for the RGB product generation. These are moved into the products section of RGB because different RGB products may prefer or require different LiDAR products for their generation. For the orthomosaic, we'll select our digital surface model, whereas the colorized point cloud requires a point cloud input. Finally, we can name and save our pipeline. Now that the pipeline is saved, if we select it, we can see a few different options at the top of this pipeline. We can edit the pipeline, export it to a file to share with others, or delete the pipeline. If we edit a pipeline and change the name, it will save as a new pipeline instead of overwriting, effectively allowing you to duplicate pipelines instead of starting from scratch. Now that we've created and selected our demo pipeline, we can select the GRAW bundle we'd like to process. Selecting the demo GRAW we created earlier, we can select the GNSS tab in the pipeline summary. Let's change our output CRS. Because GNSS can be processed outside of GRYFN Processing Tool in PostPack or Q-inertia, the GNSS processing parameters are defined at job submission time. Additionally, GRYFN Processing Tool will attempt to detect previously exported trajectories and allow the user to select a previously generated export for processing, saving time when reprocessing. Toggling Force Reprocess in the GNSS Pipeline Summary tab will submit GNSS data for processing, saving the new run in a unique project folder in the GRAW. After submitting a job to run GNSS processing, respective project files, reports, geodesy information, and more are saved in the GRAW SVG or APX folder. GRYFN format export and event files are also output in the project directory for use in later processing steps or for review by users. If users wish to process GNSS data manually in the respective software, they may do so with their desired settings and provide the GRYFN bundler with the saved project folder with the export in GRYFN's custom format. When we're submitting GNSS data for processing with GRYFN Processing Tool, the parameters available are based on the type of GNSS sensor on board the system. We've set our output CRS. Then, for SVG systems, the processing mode is chosen for us by Q-inertia, but with Aplanix systems, we can specify the processing mode. Both systems allow us to upload our own base station data if we wish. For this job, I'll let Q-inertia find the best public base station data available automatically, so we'll leave this blank. The pipeline summary page also gives us the opportunity to change any product or processing configuration for any of our sensor tasks for this particular submission without making permanent changes to the underlying pipeline. In the general settings, we have options for prepending the GPRO name to our products and appending product resolutions at the end of the file name for products with fixed resolutions. Because this GRAW has hyperspectral data, we're given the opportunity to select reflectance panel DHR files and pixels in the imagery to use for reflectance correction. Here's one of those JSON files now for our reflectance panel calibration data, where we can see some metadata like the type of panel, the serial number, and then the calibration values at each wavelength. I'll start by selecting the target files for the reflectance panels observed in this dataset. Then I'll scroll through the preview images to locate the reflectance panels. Now that we've located the panels, we'll click on Draw Target Bounds. We can hover over the information symbol to see the navigation instructions. I'll zoom in and pan until we have a clear picture of the panels. Then I'll select the appropriate target file for each panel. We'll start with the 11% reflectance panel and draw a selection of pixels on that target, making sure we have a large representative selection while avoiding the edges. Now we'll move on to the 30% panel, and finally the 56% panel. While selecting pixels on the target, we can see two graphs. The first graph shows either the radiance or raw values of our selection across the entire wavelength of the sensor. The second graph shows an R² value, or the variation between the observed data and the lab calibration data. If we're ready, we can hit Done and the selections and targets will be saved to files in the GRAW for future use in archival, or we can clear individual targets or the full image if we want to start over. You can see our target files have been saved inside this targets folder, and we have an ELM coefficients JSON and targets YAML with our target selection. Now we're ready to submit the data, which will move this GRAW and pipeline to the job queue. In the job queue, we can see how much time has elapsed, what step we're on, and a truncated tail of the logs, which will be output to the GRYFN processed folder, or GPRO, which follows the same organization structure as the GRAW. While we're in the job queue, waiting for this data to process, we can talk about the queue more. If we have multiple GRAW bundles waiting to be processed, we can set each of them up on a pipeline and submit them. Subsequent submissions will be added to the queue and begin processing when the previous submission completes, or even if it errors out. We also have what we call smart reprocessing, which means that we only reprocess what is absolutely necessary for the products we intend to generate. For example, RGB structure for motion steps take a long time. If we want to generate a new orthomosaic at a different resolution, we can use the same GPro, change only the resolution of the mosaic product, and submit the job. Because the surface model has already been processed and the structure for motion steps have already been completed, the software will move on to the product generation, saving valuable time. This also works when generating new products. For veneer, if I only output an orthomosaic but decide I want individual flight lines later, the geometry calculations have already been performed when we generated the mosaic originally, so the software will move on to product creation for the individual flight lines. Let's also take some time to look at other features, settings, and documentation for the software. If we return to the welcome screen, we can see our version number and whether any updates are available. If an update is available, we'll be prompted to download it. When the download finishes, the GRYFN Processing Tool will open your File Explorer to the download location where you can run the updater. You can also see a quick look at the recent patch notes, visit the embedded user manual, or our website. All our software documentation, as well as hardware and operations documentation, are available online for free on our Gitbook page, which can be accessed via our website. Returning to the software, let's visit the settings. We can toggle dark mode on or off, invert the scrolling direction and target selection, set the number of CPU threads to use, which can help some of the parallel processing components. We can also set default locations for a variety of settings. When these are set, the relevant file selection buttons throughout the software will take you directly to the default directory, saving a lot of time and clicks navigating through your file system. You may also remember me saying that for some supported hyperspectral sensors, the GRYFN Processing Tool can automatically convert raw digital numbers to radiance data on the fly. In order to do that, we have to set the default radiometric calibration location. This allows the software to parse this directory for the correct sensor serial numbers and find the appropriate radiometric calibration files for every collection. The radiometric calibration folder contains calibration data for a variety of exposure and gain mode combinations. GRYFN Processing Tool will bundle the correct files into the GRAW in the relevant sensors data folder. We also have a Planix and SBG defaults at the bottom, where we can hook up our GNSS processing software to GRYFN Processing Tool to handle GNSS data processing for us. We can also configure the software to be aware of individual pilots, information that can be included automatically in the mission data YAML in the GRAW. Next, we have a tab for product licensing, where we can see some information about our license and maintenance expiration date. We can also release machines here, so the license can be activated on a different machine. The last setting is for the Python script module. We can define a path for external scripts, our Python executable, and additional launch arguments. Once we have the GRYFN Python module installed in that Python environment, and we set the path to search for scripts, the software will parse those scripts and will show you the arguments that are available for each of those scripts. If we return to the New Job tab and edit a pipeline, we see that the script is a task we can add. Then we can configure the arguments for that script. This allows post-processing scripts to run in the job submission directly. If we back out of this, we can also run a script on a GPro after it's finished processing. You can find the Python module and installation instructions on our GitHub page. We just got a system notification letting us know the processing output has completed. We can scroll to the bottom of the log to see the total time to process was 78 minutes. Similar to the GRAW bundle, we also get a button to open the data products folder. The system calibration file and mission data YAML are passed through to the GPro. A manifest of all data files, raw and processed, and a manifest of products used for the Python module are created. The pipeline file and processing logs are also stored in individual folders in the GPro to keep track of processing history. Each individual sensor folder contains the intermediate products generated for that sensor. Then, the products folder contains the final data products we asked the pipeline to generate. In here, we can see our LiDAR digital surface model, LiDAR point cloud LAS file, colorized point cloud LAZ, high-resolution RGB orthomosaic, hyperspectral orthomosaic, and individually orthorectified hyperspectral flight lines. Here we've opened Cloud Compare and loaded in our LiDAR point cloud and RGB colorized point cloud. The default scalar field for the LiDAR point cloud is intensity, but it's easier to visualize if we color by height. We'll go to the scalar field settings and export the Z value as a scalar field to colorize points by height. The dataset we processed is an agriculture research field and parking lot at Purdue University's Agriculture Center for Research and Education. Taking a look at the left, we can see some information about the point cloud, such as the number of points, which is 29 million for this dataset. If we look from the top view, we can see that this product has been neatly trimmed to the extent file we defined earlier, a nice rectangular area. If we toggle the RGB colorized point cloud, we can see the LiDAR point cloud has now been colorized using the red, green, and blue values from the RGB mosaic. We can also see that this has been trimmed to the same processing extent. Now I've opened the LiDAR digital surface model, v-near hyperspectral orthomosaic, one individually orthorectified hyperspectral flight line, and the RGB orthomosaic in QGIS. Here we can see our LiDAR digital surface model processed to 8 cm resolution, also maintaining the processing extent. Here we have our nice hyperspectral orthomosaic raster. The hyperspectral mosaic has been spectrally binned by 2 in processing, so we have a raster with 172 spectral bands. If we investigate some points in the hyperspectral mosaic, we can see the reflectance values are scaled by 10,000, which we defined in our pipeline. If we toggle this, we can see our individually orthorectified flight line. We can also view our high-resolution RGB orthomosaic, processed to 6 mm. Looking back, we spent less than 5 active minutes with the software to generate a full set of research-ready data products to use in further analysis. And there you have it. With the GRYFN Processing Tool, you now have the power to efficiently process raw sensor data from hyperspectral line scanners, 3D LiDAR, and high-resolution frame cameras, converting them into valuable orthorectified products. Organizing raw and processed data alongside metadata into GRAW and GPRO folders, our software simplifies data management, ensuring your workflows remain organized and efficient. With its user-friendly interface and seamless integration capabilities, the GRYFN Processing Tool is the ideal solution to streamline your geospatial data processing needs. Thank you for joining me in this demonstration of the GRYFN Processing Tool. If you have any questions or would like to learn more, please visit our website or reach out to our team. We're always here to help. Until next time, I'm Ryan Riley, and I look forward to seeing how the GRYFN Processing Tool can revolutionize your data processing experience.